Hello friends, this is Professor Rahul Bhavne and in the subject of heat transfer, today we are going to see radiation resistance and rate of heat transfer. So in radiation, there are basically two kind of resistance. So we will check out which are those. So before that, we will see some basic terminology and basic concept. So irradiation, what is the irradiation? So in a simple language, irradiation is nothing but a radiation received by any particular surface or any object. That is called irradiation. So all receiving radiation by the particular surface is known as irradiation. So suppose there is any body or surface and radiation in all directions as well as having different wavelengths. So I am noting here wavelength A, wavelength B, C, D, E, F, like that. So all kind of wavelengths in all direction. So even though radiation arrows are different, that means these are the different radiations. So what is irradiation? Radiation received by any surface, that is called irradiation. So as per the definition, irradiation is defined as the total radiation received by a body or surface per unit time per unit area from all direction and of all wavelength. This is highlighting lines. It is not only the radiation received by any surface per unit time per unit area, but in all direction as well as all wavelength, and that total radiation received by surface is denoted by capital G, that is a irradiation. Now the irradiation is the total amount of radiation incident on a surface per unit time per unit area, but remember in all direction as well as having all kind of wavelengths. Now what is radiosity? So irradiation is a receiving radiation, radiosity is a emitting radiation. But radiosity is not only the emissions. So radiosity is mostly combined the emitting radiation as well as some radiation which is received on the surface and get reflected. Even though if you go in a depth, so some radiation which is transmitted through the surface. So surface own emitting radiation, some transmitting radiation, some reflected part of radiation, all these radiation combinedly known as a radiosity. But broadly, in most of the cases, we consider only reflected part as well as emitted part. Every surface above absolute zero temperature emits radiation, but at the same time, some radiation incident on the surface and that get reflected. So during emitting its own radiation, outside radiation which is received by that surface, some part get reflected. So that reflected part also seems to be a radiation living from the surface. So total radiation that is emitted as well as reflected part, that is considered as a radiosity. The radiosity is defined as the amount of energy emitted from a surface per unit time per unit surface area, and it is denoted by capital J. So capital G is for receiving radiation, capital J is for emitting radiation. Now absorptivity, everyone knows, we already learn in I think 12th standard itself. So whenever irradiation, that is total radiation received on any surface, so out of that some part get reflected from the surface, that is called reflection. Some part get absorbed within a body, absorbed part, and some part directly transfer through that surface and moving ahead through the body on second side. So absorptivity, that is normally denoted by alpha, and it is nothing but a amount of radiation absorbed by the surface divided by total radiation received or incident on the surface. So all these are nothing but a fraction of irradiation. So fraction of irradiation which is reflected, which is absorbed, and which is transmitted. So absorptivity on notation, mathematical expression. So alpha is G absorbed divided by capital G. So capital G is the total radiation received, and G absorbed is the amount of radiation absorbed. Now reflectivity. So some part get reflected. So mathematical expression, G reflected divided by total radiation received, that is G, and reflectivity is denoted by that is a symbol rho. Transmissivity, it is denoted by tau, and it is nothing but a amount of radiation transmitted through the body divided by total incident radiation. Now moving to our main topic, that is surface resistance of radiation. So in case of radiation, there are two kinds of resistance to rate of heat transfer. First is surface and second is space. So surface, any body or surface above absolute zero temperature, that body will emit radiation. Absolute zero, that means minus 273 Kelvin. Let the surface which receive radiation, that means irradiation, is G, and that surface leaving radiation from that outer surface or emitting as well as the reflecting part as a radiosity capital J. So that surface receiving G amount of radiation and leaving J amount of radiation. So what is the net heat transfer? So that is Q by S per unit area. So Q by A will be J minus G. So whatever be the leaving radiation from the surface minus receiving, so that much amount is actually net heat transfer to that particular subject. This is our equation 1. Now radiosity, we know that radiosity is its own emitting radiation, so emissivity of that body plus reflected amount of radiation. So reflected amount multiply irradiation by reflectivity. So we saw the formula, that is reflectivity is nothing but a G reflected divided by total irradiation G. So reflected part of radiation, so it will be G reflected, and it can be written as G into rho. So this is emissive power of that body, and this much amount is emitted by that particular body, and this much amount of radiation is reflected. Now we know what is emissivity. Emissivity is a ratio of emissive power of a body to the emissive power of black body. So from this relation we can find the emissive power of body, that is capital E, and it can be now replaced by emissivity into emissive power of black body. So our equation becomes J is equal to emissivity, emissive power of black body, plus G rho. Now we know that absorptivity, reflectivity, and transmissivity, if we combine this, so it will become 1. So for black body, transmissivity is 0. So this tau will be 0. So we remain with only alpha and rho. Now for again black body, absorptivity of any black body is always equals to its emissivity. So we can replace absorptivity by its value emissivity. So our equation becomes emissivity plus reflectivity is equals to 1. Now, what is emissivity, reflectivity? So rho is equals to 1 minus emissivity. So we can replace now rho by 1 minus emissivity. We can replace by E by emissivity into emissive power of black body. So our equation is J is equals to emissivity, emissive power of black body plus irradiation into bracket 1 minus emissivity. Now this is our final equation. Now rearrange this. So we are rearranging, shifting this. So it becomes J minus emissivity into emissive power of black body. So we are shifting this part only. So it becomes minus. Now irradiation G is equals to J minus emissivity, emissive power of black body in numerator, and in denominator 1 minus emissivity. So now we are going to put this value of G, that is irradiation, in our main equation 1. At the beginning we noted as equation 1. So equation 1 is Q by A is J minus G. Here we are going to replace irradiation G in terms of other. So this is our final form. Rearrange this. So we are taking LCM 1 minus emissivity, then calculating cross multiplication. So on simplifying, we observe that J minus J emissivity again minus J plus emissivity, emissive power of black body. So this plus J and minus J get cancelled. So finally we have only minus J emissivity plus emissivity, emissive power of black body in numerator. So if emissivity is taken out as a common, so emissive power of black body minus J. Now shifting this A, rearrange this, so it will be emissivity area, of course that is a surface area responsible for radiation, EB minus J upon 1 minus emissivity. Rearrange this. So this is our final form of a rate of heat transfer by radiation. So Q is equals to emissive power of a black body minus J radiosity divided by 1 minus emissivity divided by area into emissivity. Now suppose I am comparing this equation with our electrical system. Electrical system having a equation, current is equals to dV upon resistance, correct? So current is a flowing quantity, here Q is a flowing quantity. It is a flowing quantity by radiation. dV is the potential difference which is causing the flow of current, that is the driving force. Here EB minus J is the driving force. Because of this difference, there is a radiation, rate of heat transfer. So numerator belongs to then resistance, and this resistance is called as radiation surface resistance. So radiation having a surface resistance, and that surface resistance having a formula 1 minus emissivity divided by area into emissivity. This is radiation surface resistance. So whatever be the your surface is there, you have to note down its area and its emissivity, and by using this formula we can find out what is resistance, surface resistance for radiation heat transfer. Now the second resistance is space resistance. So suppose there are two plates, one is at area A1, temperature T1, emissivity eta 1 or epsilon, whatever you pronounce it. So second having area A2, temperature T2 and emissivity 2. Now as in a previous lecture we saw that if there is a radiation from plate 1 to 2, so we have to consider shift factor F1 to 2. If radiation from 2 to 1, then we have to consider shift factor 2 to 1. Here we are considering only heat transfer from 1 to 2. So from this plate to this, and in between there is a resistance. So this resistance will be a space resistance, the space through which this radiation passing through. So this is space resistance. Now Q1. Q1 is the amount of radiative energy from body 1 and 2 moving to body 2. So Q1 can be calculated as area 1, shape factor 1 to 2 and radiosity because it is living radiation. So J1. In the same manner, if we are talking about the surface 2, so Q2 will be the radiative energy from body 2 and receiving by body 1. So 2 to 1. So Q2 will be area A2, shape factor 2 to 1 and radiosity J2. Now the net radiative energy exchange between 1 to 2. So it will be Q1 minus Q2. I am talking only about 1 to 2. If 2 to 1, so it will be different. Notation will be Q2 to 1, Q2 minus Q1 like that. So here we are considering only net energy transfer or exchange from 1 to 2. So Q1 minus Q2. So putting the values of Q1 and Q2. So here A1 F12 J1 minus A2 F21 J2. Now we know that what is the reciprocity rule. So area A1 shape factor F12 must be equal to area of other A2 shape factor 2 to 1. This is reciprocity rule. So we can replace this A2 F21 by A1 F12 or even though A1 F12 by A2 F21. So anyone can replace. So here we are replacing this A2 multiplied by F221 by A1 F122 shape factor. Now taking this area and shape factor as a common. So in bracket there is J1 minus J2. So we got this final expression J1 minus J2 and this is the common terms. Now rearranging this, so it will be Q1 to 2 is equals to J1 minus J2 upon 1 upon area A1 and shape factor 1 to 2. Why shape factor 1 to 2? Because we are considering heat transfer 1 to 2. If we considering 2 to 1, then shape factor will be 2 to 1 and area will be A2 then. And in numerator J2 minus J1. So likewise there will be a changes. Now this is our final form of heat transfer from 1 to 2. So in a regular or without suffix, if I try to write this, so it will be heat transfer rate Q is equals to change in radiosity J1 minus J2, that is change in radiosity divided by 1 upon area multiplied by shape factor. So that will be our formula. So comparing with electrical system, what is the flowing quantity here? So it is a Q. 1 to 2 is a flowing quantity. What is the driving force? So driving force is J1 minus J2. That is a driving force. So this denominator belongs to be the resistance. And this resistance will called as space resistance. So radiation space resistance 1 to 2 is 1 upon area A1 shape factor 1 to 2. Suppose I am talking about resistance, space resistance from 2 to 1. In that case, it will be 1 upon area A2 shape factor 2 to 1. So space is same, only values get changed if I am talking about heat transfer from 1 to 2 or whether it is from 2 to 1. So accordingly we have to change the notation. In general, space resistance is equals to 1 upon area and shape factor. So product of area and shape factor, that is a space resistance. So there are two kind of resistance in radiation, surface as well as space. Now the next concept, suppose there are two surfaces and infinitely long and flat surfaces. That means complete radiation get absorbed by the second surface. So surface 1 having different property, surface 2 having different property and different shape factor. Now in this, if I try to draw electrical analogy, so obviously surface 1 having its own surface resistance. So R surface 1, this is surface resistance. Surface 2 having its own surface resistance, R surface 2 resistance. And in between these two plates, there is a space resistance. So R space. And we are talking only about heat transfer from 1 to 2. So Q1 to 2. So for very long surfaces, infinitely long surfaces, we know that then both the area will be same. So A1 and A2 are same. So we will note it as A. Shape factor for flat surfaces. So from the property, so F11 will be 0. In the same manner, F22 will be 0. Now using summation rule. So applying for first surface summation rule, because virtually all the radiation will absorb by surface 2. So it is virtual in closed loop. So F11 plus F12 is equals to 1. F11 0. So F12 will be 1. Again, either we can use a reciprocity rule or again we will apply summation rule for surface 2. So summation rule for surface 2, shape factor 2 to 1 plus shape factor 2 must be equals to 1. 2 is 0. So 2 to 1 is 1, because whatever be the radiation emitted by surface 2 totally absorbed by surface 1, because both are the same area. So we get the 100%. So it is F12 is 1, F21 is 1. Now this is our schematic and these 4 shape factor we know now. Now net heat transfer using electrical analogy. So Q1 to 2, we are only considering heat transfer from 1 to 2. So sigma T raised to the power 4. So here T1, because considering 1 to 2, so T1 raised to the power 4 minus T2 raised to the power 4 divided by total resistance. This is our generalized formula. Now total resistance consists of surface resistance 1 plus space resistance plus surface resistance 2. Now surface resistance, as we know, 1 minus emissivity upon area into emissivity. So 1 minus emissivity 1 divided by area A1, emissivity 1 plus space 1 upon A1, shape factor F1 to 2. Why this space resistance having this notation? Because we are considering only 1 to 2. If heat transfer 2 to 1, so space resistance will be different. A2, F2 to 1 will be the space resistance in that case. Okay, now move ahead. So surface resistance 2, 1 minus emissivity 2 upon area A2 multiplied by emissivity 2. Now here we are considering large infinitely areas. So A1 and A2 are same. So we will replace that notation. So here A, again A and A. So we can take out A as a common. So it will be 1 upon A. And if I move it, shift it to numerator, so it will be in multiplication with sigma. So Q1 to 2, sigma, area, temperatures difference. But remember, whenever there is a problem of any kind of radiation, so we have to put the value of temperature in Kelvin only. So T1 raised to the power 4 minus T2 raised to the power 4 divided by 1 minus emissivity 1 divided by emissivity plus 1 upon shape factor 1 to 2 plus 1 minus emissivity 2 divided by emissivity 2. Now shape factor 1 to 2, we come to know that its value is 1. So it will be 1 upon 1, that means 1. Now separating this. So 1 upon emissivity 1, emissivity 1 upon emissivity 1. In this term also in a numerator, 1 upon emissivity minus emissivity 2 upon emissivity 2. So it will become like in numerator it is remain as it is. In denominator 1 upon emissivity 1 minus 1 plus 1 plus 1 upon emissivity 2 minus 1. So plus 1 minus 1 get cancelled. So the final form for this configuration, rate of heat transfer from 1 to 2 is sigma surface area T1 raised to the power 4 minus T2 raised to the power 4, denominator 1 upon emissivity 1 plus 1 upon emissivity 2 minus 1. In case suppose I am calculating for heat transfer rate from 2 to 1. So what will be the changes in the formula? So 2 to 1, so sigma area T2 raised to the power 4 minus T1 raised to the power 4. Here sigma 1 upon emissivity 1 plus 1 upon emissivity 2 minus 1, it will remain as it is. So that will be only changes. Now the one numerical on this topic, this will be our last portion for today's lecture. So statement is given like find the rate of heat transfer due to radiation between two infinitely long parallel plane. One plane has emissivity 0.4 and it is at temperature 200 degrees centigrade. Other plane has emissivity 0.2 and at a temperature of 30 degrees centigrade. So we know emissivity 1 is there 0.4, temperature T1 200 converted into Kelvin. Emissivity 2 is 0.2, temperature 30 converted into Kelvin. Now rate of heat transfer between two planes. So for such configuration where there is a surface resistance 1, surface resistance 2 and space resistance and heat transfer rate from 1 to 2. So we just derive this formula, but they don't provide area. So in such case, either we must write down for unit area, area is equals to 1 meter square and then put the value area is equals to 1, or we shift area term. So Q by A, so Q by A 1 to 2. Remember, whatever be the notation is there, that direction heat transfer rate we are calculating. So Q1 to 2, so Q by A 1 to 2, sigma T1 raised to the power 4 minus T2 raised to the power 4 divided by 1 upon emissivity 1 plus 1 upon emissivity 2 minus 1. Sorry. So we know the emissivity and temperatures, put the values. Then after calculating, we come to know that Q by A, that is heat transfer rate per unit area from surface 1 to 2 is 363.11 watt per meter square. This will be our answer. So I think this is clear your idea how to use electrical analogy in radiation. Secondly, what kind of resistance are there in radiation? So remember, surface resistance and space resistance. Okay. So thank you.